and welcome to the April 2025 edition of the IoT Security Foundation webinar series. We've been going with these broadcasts since January 2023, so we've got quite a handsome archive of recordings now. If you're an IoTSF member, you can watch them all. Just go to the messages section of the plenary on our members platform. If you're not an IoTSF member, you can watch shortened versions of past webinars on our YouTube channel. If you're watching this live, I'll put the link in Zoom chat in just a few moments. If you're watching the recording of this, then it means that you've already found us on YouTube. So please like this video and subscribe to the channel. It helps us out a lot. So just whilst people are arriving on Zoom, I want to tell you about an IoTSF event that's happening in Bangalore. The event title is Cybersecurity for Connected Transport, Securing Avionics, Rail, Marine and Off-Road Systems. It takes place on Saturday, 17th of May at the premises of Sasken Technologies. That's in the Domlur area of the city, and registration is limited to 150 people. Now, the IoTSF events in Bangalore, they always sell out, so please register now if you'd like to attend. If you're watching live, I'll put the link on Zoom chat. So coming up soon, we'll have PQC Transition, What You Need to Know in 2025. That's by Daniele Fronte of Seal SQ. But first up today is Dr. Ramy Shelbaya of Quantum Dice, a physicist by background. Ramy co-founded Quantum Dice right after completing his DPhil, Doctor of Philosophy, in atomic and laser physics at Oxford. Having previously worked on a wide variety of applications in quantum technologies, ranging from computing to communications and sensing, Ramy has a passion for communication and for the commercialization of scientific breakthroughs. Ramy has been leading Quantum Dice ever since its original inception, focusing on ensuring the alignment between the technology development and the needs of the market, whilst ensuring Quantum Dice's continued growth. His talk title today is The Critical Role of Randomness in IoT Security. If you have any questions or observations about what you're about to hear, please put them in Zoom chat, and we'll put those to Ramy during the Q&A section at the end of today's broadcast. That's enough from me. We now cross over to Oxford in England. Ramy, the floor is yours, my friend.
Thank you very much for that incredible intro, Chris. I hope that people don't feel that you oversold them a bit on the content, on the quality and the content of the presentation. But yeah, it's a pleasure to be here, and thank you so much for the IoT Security Foundation for giving us this venue to talk more about our technology and the benefits that it will bring for IoT security. And on that, I'm going to start my presentation. All right. So as Chris was mentioning, my talk is going to be focusing on the critical role of randomness in IoT security. And to understand that, before that, I'm going to just give a quick overview of Quantum Dice. So we are an Oxford University spin-out. We came out of the university's Department of Physics. And ever since our original spin-out, we have been able to assemble an incredible team of exceptional scientific, engineering, and commercial talent as we tackle one of the most fundamental challenges in computing. We have been backed by a consortium of European VCs who have given Quantum Dice the ability to not only grow our team, but also to take our technology to market, working with major companies in the UK, in the US, and in Asia. Some of the names that we've been working with are companies such as BT and HSBC. Additionally, Quantum Dice has been fortunate to be recognized through numerous awards, including being selected as one of the UK's top 100 startups 2 years in a row. With this year, we have climbed up to number 7 in the rankings. And so the core of our technology is powered by some incredible leading research that was done originally in the quantum optics department at Oxford, back when it was led by Professor Ian Walmsley. So to start with, let's talk about IoT. So IoT has made our lives so incredibly convenient. Just on one simple device, just on your phone, you have your wallet, you have all of your essential documents. You have almost the entirety of human knowledge at the touch of your fingertips, which is an incredible achievement and an incredible testimony to how rapidly technology has developed over the past century. Not only that, if we think about it and where it's going, a phone is way too big, a phone is way too complicated. Just on a simple card now, people are looking to put everything from our passports to our medical history, all in the convenience of something that you can place in your wallet. However, that convenience is sort of a Trojan horse. All of these devices that we keep deploying everywhere, all of these small little connected systems that are making our lives so much more convenient, also make our lives convenient for others to access in an unwanted way. Now, a simple example is we basically, each of us now has a bunch of devices in our homes that can effectively serve as surveillance equipment. Now, I know that sounds like fear mongering, but the reality is we have to consider where each one of these devices is placed and what are the kind of vulnerabilities that are associated with them. Now, if we think about security, security is a very complex beast composed of many, many, many different layers. At Quantum Dice, we are focusing on the fundamental cornerstone of security, and that is randomness. I know when we think of security on a day to day basis, we usually consider some of the more larger scale, higher level systems, whether that's encryption systems, whether that's cryptographic protocols, whether that's the way we communicate. But beneath all of these layers, at the core of any of them, requires the ability to generate randomness. And this is because randomness is the tool that we use to create all of the different functions that are accomplished in any kind of cryptographic system. Now, the fact that randomness is essential is, of course, no news. Just a few years ago, ATIS, so the main organization in North America for the standardization of telecommunication systems, wrote up a paper on the importance of entropy, not just for the current generation of encryption, but for the new generation of cryptographic protocols that are coming to head. Now, entropy here is just a more technical term to refer to the same concept of randomness or unpredictability. Now, with IoT devices, they are particularly vulnerable to the sort of issues that are related to the difficulty of producing correct and reliable randomness. So it has been shown multiple times that there are numerous incidents that are intimately tied to how we can actually secure systems within IoT devices. So, for example, back in 2013, there was an issue with the Taiwan smart card system that they developed. So, that smart card was to serve as a repository of all of your government data. Now, unfortunately, what they found out is that the randomness generation that was happening on those cards, the core functionality that would enable all of the security features of that card, was not even minimally good for the job. Now, this isn't just a unique situation, but this can highlight how a simple thing on such a critical component can affect so many people. This ended up resulting in a recall of tens of thousands of these cards to try to fix the fundamental core issue. Now, this isn't just limited to this example. So, a few years ago, also, Key Factor made some research on what if we took all of the RSA keys that are out there on the internet, so the ones that are publicly available, and took a look at how many of them are actually fit for purpose. And what they found was that a considerable percentage of those keys that they found in the wild did not have sufficient entropy, did not have sufficient randomness to actually be secure. Now, I know 1 in 172 does not sound like a large number, but you have to realize that there are millions of these keys out there. So even 1% of them is a tremendous amount of entry points that are now not secure because of the way the entropy was generated originally. Now, why is this challenging? Why is it so hard to make something that is random? Well, to see that, it's instructive to try to understand what is randomness to start with. So if I show you this stream of digits, can you predict what comes next? Now, this looks pretty random. It looks like there is no discernible pattern. And I know that my slides have failed me here, but basically what this is just an extract from the digits of pi. No, not only do we know what comes after 9, it's 5, by the way, we know what comes after it for a million other places. Pi is a completely predictable sequence that comes from a fundamentally mathematical formula. So even though a part of it might look random to us, fundamentally it is incredibly predictable. And now, this is not just a visual trick. It is very important to stress this. This is intimately tied to the challenge of figuring out whether something is random just by looking at it. So, if I take a million digits of pi and put it into one of the standard tests that have been designed to try to tell if something is random or not, it would actually tell me that what it is seeing is random. And that's because these tests, like any other test that tries to look at the output of a system and figure out if it's random or not, is not something that is capable of telling us anything other than the statistical features of the stream. It cannot tell us anything about the unpredictability of that stream. And this is where quantum dice's solution comes into play. We have developed what we call the source device independent self certification protocol. And like anything invented by physicists, it has a horrible name. So we just gave it the nickname DISC. Now, DISC is basically a combination of a hardware architecture that relies on quantum mechanical processes, not only to produce randomness, that's something that many other things could do, it is able to give you a continuous live measurement of the amount of randomness that is being produced at any given moment. Now, it's important to stress this isn't a statistical estimate. This is not a statistical test. This is a direct measurement coming from the quantum process itself, leveraging some of its incredible features to allow us to give a level of assurance never before seen in a random number generator system. So this is a patented architecture that we developed at the University of Oxford and that Quantum Dice is taking to market. So let's talk a little bit about how does that make us different from the classical systems. So if we compare to what is currently the state of the art, what is the primary difference? What is the quantum advantage? Well, right now, all entropy sources on the market in IoT systems are fully device dependent, which means they are completely dependent on the components, the hardware components that are enabling them, which means any changes in the environment, any changes in the hardware over time is going to impact their quality. And as we have seen with the Pi example, it is not easy to figure out if something works just by looking at its output. With quantum dice, we don't have that same problem because our system is source device independent. This also allows us to do a continuous, true real-time monitoring, something that is just not possible with classical hardware where you have to rely on kind of statistical tests. And this means that with our disk protocol, each individual bit that is produced allows it is reliable and fully meets what you need from it in your system. And not only that, we can achieve with this an incredibly high speed. So this system can scale for whatever your use case requires. We have to realize that as time goes on, as encryption systems get more sophisticated, their demands on entropy are getting stronger. Now let's take a more concrete look of what exactly does this mean. So if we compare between a quantum source and a classical source, especially, what does this protocol offer? So in both cases, you're going to produce some keys. You're going to produce some entropy. Now, sometimes those keys can be bad, and sometimes they can be good. It's all dependent on how the hardware is operating. With a classical system, all you can do is run a statistical test. And like we know with any statistical test, it doesn't look at each individual output. It looks at the collective output. So if most of them are good, it's just going to accept them. But with our disk protocol, each individual output is qualified and quantified to check if it is fit for purpose. And if it's not, it is not. And that allows us to only produce keys that are truly fit for purpose for your usage. No more of the same problems that were identified originally by key factor. Now, if we take a look, of course, at an example where most of them are bad, in this case, the statistical test is going to work just fine, right? The statistical test, if everything is not working well, or if most things are not working well, the statistics are actually going to be in your favor in this case and will be eliminated. But that isn't what you want. You don't want something to work most of the time, or you don't want something to work on average. At the end of the day, with cybersecurity, like with any kind of protection, it's not how many times it works, it's how many times it doesn't. Because an attacker only needs to succeed once, while your system needs to be safe always. Now, I know that when I talk about quantum technologies, most of you picture something like what's in either of these two images, either a gigantic dilution refrigerator containing incredibly sensitive components that need to be maintained at an incredibly cool temperature in order to operate, or having potentially a photonic system, an optical table filled to the brim with dozens and dozens of mirrors that some poor PhD student spent a couple of months aligning. Well, the reality is our technology used to look a bit similar to the one on the right. However, right now we have managed to put all of our systems, all of the different elements that make up our quantum photonic system on an individual chip. So what you see in the picture here, right underneath this pound coin, is our photonic integrated chip. So on this millimeter scale chip is contained every single component that allows our system to be source device independent and to produce entropy at an incredibly high rate and with an incredible, unprecedented level of assurance, which means that we are moving towards a day when you can have this chip in every single system out there, when your phone can be as protected as it needs to be. Because remember, your phone is no longer just your phone. It is your wallet. It's going to be your passport. And who knows what else it is going to have to protect. Now, this isn't the only way you can distribute quantum entropy, quantum assured entropy to the kind of devices that make up the IoT sector. In fact, you don't even have to think about hardware for that. So one of the other approaches that we have developed is what we call the quantum entropy as a service. So this is a system that was originally developed by the National Institute for Standards and Technology with their entropy as a service concept. And we took that concept and upgraded it with our hardware to enable the secure distribution of quantum entropy, as well as all of the associated metadata that gives you that assurance that I was talking about earlier with the disk protocol, all the way to the endpoints that need it. So the way it works is you have multiple different servers located around the world and located in different locations that can be connected to by every kind of different device. And these servers can distribute to those devices the entropy, the components that they need to enable their cybersecurity. So a single device would call upon multiple servers, combine the output that comes from them in order to obfuscate that system, and then run an extraction protocol and produce ready random keys for their encryption protocol. This means that even very, very low resource IoT devices are able to produce the entropy that they need to run the encryption systems that they need to run. And now you have to think about this. Low entropy, low resource IoT devices are not just simple devices that we don't care about. These could be cameras out there protecting our systems. These could be sensors that are collecting very, very sensitive data that you don't want to get into the wrong hands. These could be autonomous systems that need to be quite secure in their communication, or else they could be provided a vector for somebody to access and control. So low resource devices are low resource not because they are of low importance, they're just low resource because of the nature of where are they deployed. And something like this would be able to communicate to those devices, to send to those devices all of the entropy that it needs without having to change the hardware itself. So with both of these approaches, with the hardware chip that can be directly integrated into the next generation of IoT devices, as well as the entropy as a service that can connect to the existing generation and provide it with the entropy that it needs for cybersecurity purposes, our goal is to provide every single device out there with the raw material it needs to enable it to run encryption successfully. And this is the time to start adopting. So this technology, as opposed to other quantum technologies, is not something ahead in the future. It's not something where we still don't know if it is going to work. It works, it can be deployed, and it has been deployed. So now is the time to think about how can this be used to better enable security for IoT systems. And at this point, I'd like to thank you all for listening, and again, thank the IoT Security Foundation for giving us the opportunity to talk a little bit more about our technology and elaborate about its potential use cases and benefits. So thank you very much, Chris, and back to you.
Thank you very much, Ramy Shelbaya of Quantum Dice. Questions already coming in nicely. You've even got a little round of applause emoji on Zoom chat there, Ramy. Any questions about what you've just heard, or any observations, comments, blah, 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 please put them in Zoom chat, and we'll put those to Ramy during the Q&A section towards the end of today's broadcast. The IoT Security Foundation will be holding what we're calling a town hall and networking event in England at Coventry's MTC on Tuesday, the 3rd of June, and we'd like to invite IoTSF members and interested parties to this very special event. Peter Davies of Thales will be a featured speaker. We'll have project updates, we'll have memory safety, that will also be under the microscope. There'll be updates and shared perspectives. We'll be workshopping future roadmaps, and we'll hear new ideas from our Smart Built Environment Working Group, the Regulatory Watch Working Group, and our Assurance Framework Working Group. If you're not an IoTSF member but would like to attend, please contact myself. It's chris.benison@iotsecurityfoundation.org if you'd like to enjoy this valuable day of networking and hear about the very latest happenings in IoT security. If you're watching the recording of this webinar, please go to the events section of iotsecurityfoundation.org. If you're watching this live and you're an IoTSF member, I'll put the link to register in Zoom chat in just a few moments. Up next, we have PQC Transition, What You Need to Know in 2025 by Daniele Fronte, PhD, of SEAL SQ. I was about to introduce Daniele in my best French, but he's going to have a bit about himself on his first slide. So let's get into it. We now cross over to Marseille, and if you've got any questions for Daniele, again, put them in Zoom chat. But for now, vas-y, Daniele.